So it's a joint work with Viktor, Vafeiadis, Jeehoon, Kang, Jeehoon, and Dreyer. And let me start with some background of the C11 memory model. One of the basic observations is that there is no one particular consistency level that is always what we need. Sometimes we need strong consistency. Sometimes we can get along with weak consistency guarantees for shared accesses. And accordingly, we have four main access modes for shared memory accesses, going from non-atomic accesses that are very efficient, very cheap to implement, but provide absolutely no guarantees in the case of data race. And through relaxed accesses, release acquire accesses, and finally we have these SE accesses. These are sequentially consistent accesses, the strongest consistency guarantees they give us. They are most expensive to actually run, and they give us sequential consistency, basic interleaving semantics. Now the point is that sometimes we can get along with weaker things, sometimes we need this SC. And these are two examples to demonstrate this. So this is a very common idiom in concurrent programming, message passing. You have two threads, this thread sets X to 1 and then Y to 1. The other thread reads Y and then reads X. So I assume the initial value is zero for all occasions. And you see I use the SC annotation. So you can think about interleaving semantics if everything has SC annotation. And this behavior described here by these comments, that here I read 1 and here I read 0, is disallowed obviously under interleaving semantics. If I see this Y1, I know about this one, this thing happened before, so I will read X1. But if this is the thing that I need, as happens many times in concurrent programming, I can actually get along with much weaker accesses. I don't need SC, these are too strong and too expensive. I can get along with relaxed accesses for X and release acquire for Y. There are, however, cases like this store buffer case that if I try to weaken any kind of weakening, so these two programs here are equivalent. They have exactly the same behaviors. But here, any kind of weakening that I try to do will allow this behavior that both of these are 0. And if the correctness of my algorithm, what will happen, for example, if it's a Decker critical section, if depends on the fact that none of them is reading 0, I will have to use these SC accesses, because if I try to weaken this, let's say to release, now this behavior becomes allowed. So this work is mainly concerned with this part of the model, this SC accesses, that seems simple, but in connection with the others is actually quite complicated. And so first we observe that SC semantics in C11 is too strong, and this is a new correctness problem in the specification. There were proofs or claimed proofs for correctness of compilation of C11, and this is wrong because the specification is too strong. And second, we observe on the other side, it's also too weak, and this has to do with SC fences. And for both of them, we show how to get the SC semantics just right, how to fix this correctness problem and strengthen the semantics for the SC fences to get better guarantees from them. And in the final slides, I will speak quickly about relaxed part of the model. So this suffers from the outer thin air problem. And here in this work, we use the opportunity and we prove the correctness of a conservative solution for this problem that has some cost. Okay, let me start with the first point. So I'm saying that SC semantics is too strong. And this is an example that demonstrates this one. So let's see what happens here. We have 4 threads, and there are 2 writers and 2 readers. The writer here sets X to 1, and the other one Y to 1. And this here reads X and then reads Y, and this one reads Y and reads X. Now, if you think about interleaving semantics, this is disallowed. You cannot get here 1 and 0 and here 1 and 0, simply because if this one happened before this one, then if I read the Y1, I will also read X1, and similarly, if this one happened before this one, I will get here, and I get here 1, I must get here 1 as well. I cannot get this behavior. This is not precisely sequential consistency because I use here these acquire annotations, but still C11 disallows this behavior. So the specification says that the program cannot show this behavior. Now let's see what happens if we try to compile this program. In particular, we are trying to compile it to the power architecture, and we follow this compilation scheme. So a relaxed read, we don't have it, but just to to build it gradually, a relaxed read is compiled just to a machine load. A relaxed write just to a machine plain store. Now, if you have an acquire, you have to put this LW sync after the read. This is one option you can go with. There are others. This is a lightweight barrier in power that will make this read slightly stronger. It will be able to serve as an acquire read. If you, in a relaxed write, you put LW sync before the store. And the point about the SC accesses, there are two ways how to compile them. You can choose either you go with this compilation scheme that is called leading sync. So sync is the strongest barrier that power gives us. And this means that before every SC access in your program, you put a sync. So you have a sync before the load and a sync before the store. In this case, you don't need the LW sync because the sync is already stronger. If you go with a trailing sync, similarly, you have to put a sync after every SC access globally in the whole program. Now, we can compile this program up here using the trailing sync convention. And this is the program that we get, a machine code. And the problem is that power allows this behavior, the same behavior that is annotated up here. And now to see this, without going into the details of the power model, it's actually it looks quite weird. Look, all the syncs here appear in the end. So these barriers, they have actually no effect. The architecture can execute all the rest of the program and in the end do these things in any order it wants. It doesn't have any effect in this case. And just having the lightweight sync is not enough to disallow this behavior because power is a non-multi-copy atomic hardware that allows this kind of behaviors to appear if you don't have the sync barrier. So this is the correctness problem, and this example is due to Yatin Menarker from Princeton and his group. And they found this independently. It's a very nice, simple example. In the paper, we show other examples that show actually also the unsoundness of leading sync compilation. And this is the one that is actually implemented in existing compilers. They compile C and C++. And in fact, even if you place a sync both before and after, it's not giving you what is promised by the specification. So it's not clear how to fix the compilers in the sense, what can I do there to get a compilation scheme that will give me these very strong guarantees. In particular, the program before will never show this behavior. So what we suggest in this work is to actually weaken the standard a bit in order to fix this correctness problem. Okay, now I have to go into the details of C11. It becomes a bit technical. So let's understand now why do I say that C11 disallows this behavior. So it tells us it's a declarative model. It means you want to check some behavior, you have to construct a graph. The graph looks roughly like this. For every access we have, so it's not a graph for a program, it's a graph for a particular behavior. So we have a value for every access. So I want here to read X acquire 1, and later to read Y SC0. The value 0, and I have here also the implicit initializations of that. I assume everything is initialized to 0, and I get the program order from the program. And now I want to check if it's allowed or not. So I'm doing it in several steps. The first step, I have to choose, every read has to be justified. I have to choose where do I read this 0 from, and actually there is only one option for every value here, so I get this reads from relation. This read reads from here, this one is reading from here, and so on. And now I'm continuing to the next stage. It tells me you have to calculate the important relation called happens before. So these are the rules how to calculate happens before, some simplification of them. If you have a program order between two accesses, then you have happens before. If you have reads from between a write that is at least release, either release or SC, and a read that is at least acquire, either acquire or SC, then you have synchronization, and this induces this happens before, and the happens before is transitive. If you have happens before, you can do it in one step. So I'm not going to add all these arrows to the graph, but some of them, in particular, we have this happens before here, because we have here SC, and here we have acquire, so there is a synchronization. Similarly in the other side. Now, the next step, and here I deviate a bit from the usual presentation of C11, has to do with the per location conditions. It's still very local. You have to check that every location, I deviate a bit from the presentation, but I will get exactly the same model. So every location behaves like SC. So look at this graph that we have. Add all the reads from edges and that happens before edges. And consider, let's say, the location X first. We restrict the graph only to X. We still have this happens before here that is because of the read of Y in the graph for X. And we have to check that this is sequentially consistent. What does it mean? There should be a sequence. We should be able to order all these accesses in one sequence such that every read reads from the last write, just an interleaving semantics. And here we can do that. In fact, we can do that only in one way. So this has to be first, the initialization, of course, and then the read here that reads 0. This is third, and this is the last one. This is our order for the location X. Similar, we didn't have any choice here. We do the same thing for Y, and we can introduce in this graph this SC per loc relation, the relation that we got by doing this calculation. In particular, this access to Y is before this access to Y in this relation SC per loc, sequential consistency per location. Now, the last step, that is actually the most complicated one, is what about these SC accesses? So far, there was nothing special about them, and this is a global condition. You have to check all the SC accesses in your program. Here in this case, we have 4. And you have to find a total order on all of them such that satisfies these conditions. So if some access happen before some other access, both are SC accesses, the SC order must go in the same order. And in the other side, if you have some access to X, so this star here is either a read or a write, and it goes to a write to X, both are SC, and you already concluded that you have SC per location between these two, then you have to take the SC order in the same order. In particular, what we get here is we are unable to find such an order because we get a cycle in this relation here. Here we have happens before from this write to this read, so we must put this one before this one. From this read to this write, we have the SC per loc relation, again happens before, and SC per loc. So we have this cycle here, and it means obviously we cannot find the total order that will extend this. This is not a partial order, and the behavior is disallowed. So it was the explanation why C11 disallows this behavior, and now it will be easy to see how do we suggest to fix the specification. So what I want to blame, if we think about the compiled program, and we think about the trailing sync compilation scheme, where would be the sync when we go to hardware? The sync would be after this write and after this read in particular. On this path here, between this write and read, and this happens before path, there is not going to be any sync fence, any sync barrier. And however, the model tells us that this has to be before this one. So this is going to be, this edge and this edge are going to be the ones that we would like to remove, the ones that cause the problem. Where can we still assume that we will have a sync, on what kind of paths? And the observation is very simple. If the path starts both starts and ends with program order, then when compiling the program, we will have a sync fence. Accordingly, we suggest to replace this rule here by these two. So if you have a program order between two SC accesses, yes, you have to put this one before this one, because there will be a fence, there will be a sync fence in the compilation between them two. Now, in the other condition, if you have a program order and then happens before another program order between two SC accesses, then you have to put the SC order should agree with this relation. The reason is, let's see, if we are following the trailing sync compilation scheme, we are going to have here on this edge, we are going to have the sync fence, and we are following the leading sync, the one that put the sync before every SC access, we are going to have the sync on this edge. So if we want to support both compilation schemes, we will have this condition that will will guarantee us that we have a sync anyway on every such path. So this is the change, the suggested change, and now we will not have these conditions. You cannot find one of these two paths between this event and this event, and we will say that the behavior is allowed just like the hardware does for the compiled program. So what we proved about this model, we proved on the one hand this model is not too strong. We fixed the correctness problem, and we proved the correctness of existing compilation schemes to both Power and ARMv7, both of the leading and the trailing sync compilation schemes. The compilation to TSO remains correct. There was no correctness problem for TSO. and we just weakened the model. And we also proved that various soundness of various compiler optimizations, all those that were proved sound for the original C11 specification. So now, how do we know that the model that we get is not too weak? This is more difficult to justify. So what we proved is the basic guarantee that you have from C11 programs, assuming there are no relaxed accesses. This has to do with the thin air problem that I'll say a few words about it in a few slides. The DRF guarantee says that if you have a program that has no races on sequential consistent accesses under sequential consistency semantics, then you know that you have only sequential consistent behaviors. It means that if you program carefully enough, you can use the other sort of accesses in a way that will still guarantee you sequential consistency semantics. In particular, one simple result is that if everything is sequentially consistent, marked as SC, then you get SC behaviors. There was never a problem with this. So we still have this guarantee in our slightly weaker model. And the other observation is that this model, our weaker model, coincides with C11 if you have programs that non-mix SC accesses and non-SC accesses. So positively, if the SC accesses are to distinguished locations, you never have SC and acquire to the same location. So if you keep insisting on this kind of paradigm, then you will get, our model coincides with the existing model. Okay, now a few words about SC fences, the other side of the coin. I would like to, I'm claiming that the semantics of SC fences is the other side, too weak, and show how we suggest to fix it. So what are SC fences? It's another way to guarantee sequential consistency in some sense. So we have this program that under sequential consistency, you cannot read 0 and 0 here in both of them. So how can I get it? I can either put all my accesses to be SC. As I said before, this will guarantee that you can interleaving semantics, so you cannot get 0 and 0. On the other option is you can use the relaxed accesses, let's say, but you have to put a fence, a strong fence, a fence in the source code, a SC fence. And actually I save a bit, because here in the compilation there will be only two fences, one in every thread, and here there will be 4 of them, one before or one after every access. And what is the problem? The problem is that SC fences, even if you place it between every 2 commands, if you follow the C11 specification, are not enough to restore SC. And this is a well-known example, very similar to the example I had before. Everything is relaxed accesses, and I have a fence between every 2 commands. So there is a fence between these two, a fence between these two. And C11 specification still allows this behavior. So with just using fences, you cannot get SC, you cannot guarantee SC for the whole program. And in fact, algorithm designers, it's a practical problem because they have to unnecessarily strengthen the access modes, and this leads to redundant fences. In particular, we observed in the case of Chase-Lev concurrence DQ, it's a citation from this paper of Le et al. From 13, that they have unrecoverable overheads in the interaction between atomic operations and memory barriers in C11, and this is precisely for that reason. The C11 fences are not strong enough for them. So here is our suggested fix, and I'm not going to go over the details here. It's again quite technical, but we suggest a way to strengthen the specification and while still preserving the correctness of the existing compilation schemes and the compiler optimizations, even though the model is stronger. So you get stronger guarantees for free. And now we prove that SC fences between every 2 accesses is now enough in the fixed model to restore SC, to guarantee only sequential consistent behaviors. This summarizes the sequential consistent part of the consistency part of the talk. I'd like to say a few words about the thin air solution. We took here a conservative solution. So what is the thin air problem? It has to do with these relaxed accesses. And relaxed accesses in C11 are overly weak. They allow these values to appear out of thin air, and this would be an example. In this program, the specification allows to read 1 and 1, even though 1 is never mentioned anywhere in the program. And they also break the DRF. So here in this program, if you think about interleaving semantics, there is no data race, but still the specification allows in behavior that is not explained by SC semantics. So there was a suggestion, straightforward suggestion how to avoid this thing. It has some implementation cost. This is why I call it a conservative solution by Bohm and Dembski in 14. And this is simply to require the acyclicity of program order and reads from. Actually, to prevent the hardware and the compiler from reordering a read, a load, and a store. And if you want to do that, you have to use a slightly more expensive compilation scheme. It will solve a lot of problems, but you have to either put a fake control dependency after every relaxed read, so the hardware will not reorder this for you, or a lightweight fence, I think here about power, before every relaxed write. So we use the opportunity of working on correctness of C11 specification to actually prove the correctness. It was claimed but was never proved to be correct compilation scheme, correctness of number 1 here. And we proved it both for power and ARMv7. And in fact, that was a most challenging proof in this paper. And the reason is that the hardware model does allow these cycles in program order and reads from. But we want to show that every behavior that the hardware allows, also the C11, the source allows. And we have somehow to untangle these cycles in order to show that the program was racy and it already has undefined behavior in that case. So this is a quite tricky kind of proof to do. To conclude, we presented the model we called RC11, repaired C11, that has weaker semantics for SC accesses, stronger semantics for fences. This is an orthogonal point. You can have it or remove it, disallow these PO and RF cycles. And we proved the correctness of compilation schemes, the correctness of compiler optimizations, and the programming guarantees that I mentioned before. DRF, and if you have a fence between every 2 accesses, then you have SC. That's it. Thank you.
Just to clarify, I really like this, but another way you could fix the original problem here, presumably, is by strengthening the acquire and release implementations used for fences. It's usually done on ARM anyway, I think, but not on power.
ARMv7, yes. You could make the release and acquire actually to be compiled just like SC accesses in some sense with a very strong fence. Make them more expensive, and then you avoid this problem in a different way. Yes, thank you.
Great. Other questions?
But you are going to say that nobody would ever want that.
I was waiting for you.
Well, it depends on power and GPUs. Nobody would want that. That's the problem. On ARM, that's the case.
Yeah. So for ARM. I have this complicated slide here. For ARM, there is, if you don't use the ISB, meaning you use actually the strong fence, there is no correctness problem for the original C11. If you do use the ISB, you reach the same kind of problem. Yes. Thanks. I don't have time to explain this, but I'm very happy to do it later.
Great. Other questions? All right, I have one, probably a quick one. So you talked about the equivalency in terms of correctness of the leading sync versus trailing sync compilation schemes. I wonder, so in TSO, there's sort of significant performance ramifications whether you put the fences on the stores versus the loads. Is there any reason why you might prefer leading sync versus trailing sync in an implementation?
So it's a good question. I think it's some historical decision without any good reason behind it. I'm not sure. But the compilers actually implementing this leading sync compilation scheme. Sorry? The C compilers, GCC and LLVM. And while assuming that programs usually have more loads than stores, it's actually more expensive than going with this one for the same reason you mentioned for TSO, because here you save some LWC. So I think it makes sense to change the compilers at some point to use the trailing sync compilation scheme. Yes, thanks.
All the Java compilers do the right thing.
This is controversial. We've had this discussion. The current situation, I think, is a mess.
Yeah, importantly, it has to be consistent globally in the program. If you mix these two, you run into correctness problems immediately, yes.
Okay, fantastic. Let's thank Ori again.
Thank you.